I've never been there.
Okay, so let's take a look. All right, so we've already looked at some of this stuff. I want to add some additional information, though. We already talked about isosceles triangles a while ago. And we said, remember, that isosceles triangles are triangles that have at least two congruent sides. So real quick, is an equilateral triangle isosceles?
Yes.
It is, because it has at least two congruent sides. It actually has three, right?
Yeah, buddy.
So an equilateral triangle is a special isosceles triangle, but it actually is an isosceles triangle. Normally, we associate isosceles triangles with triangles that only have two congruent sides and then one that's different, but it doesn't necessarily have to be that way. Now, in sort of a normal isosceles triangle like that, here's how we would describe the anatomy. We've talked about this. So we've got the two congruent sides we call the legs, and the one oddball side we call the base, right? We're going to add something else here that we didn't talk about before. The base angles, we're going to call the angles opposite the legs. So they're the angles that look across the triangles at the legs. The way to remember also that they're base angles is that they sit on the base, right? They are next to the base, those angles, those two angles. Okay, so, and then we say this other angle we call the vertex angle. Okay, the one that looks at the base instead. Okay? Now, what do we know about these isosceles triangles? Well, here's something we're going to add. The base angles theorem. The base angles theorem just says, and this is really useful, it says that if two sides of a triangle are congruent, so in other words, if you have an isosceles triangle, then the base angles are always congruent. So the angles opposite the legs in an isosceles triangle, the base angles, we always know are congruent. So I could write in that congruence. There it is, right? Okay, there's the base angles theorem. That one we can also flip around and use its converse. Its converse is also true. If two angles in a triangle are congruent, then we know it's isosceles. And so we can also conclude from that that the legs opposite those angles are the legs of the isosceles triangle, and they're congruent. Okay? So that's helpful. Goes both ways. So some more stuff you can use in your proofs too. Okay, so I want to show you one proof here, just because it's a little bit different than the other kinds of proofs that we've talked about. This is a little bit new. What if we want to prove the base angles theorem? So we're just given some triangle ABC, and we know that side AB is congruent to side AC. Okay, and that's marked on here, isn't it, with our congruence symbols. Okay, now what if we're trying to prove here that the base angles B and C are congruent? Now look what we can do. This is kind of slick. We haven't done this before. We can literally add some stuff to our picture. We can say, okay, we're going to go ahead and add a line segment in this case from vertex A down to the opposite side, the base of this isosceles triangle, and we'll just say that where it intersects the base, we'll call that point D. Okay, now we're going to draw this. We're going to add this segment, though. We're going to specify that when we add this segment, we want it to bisect the big angle CAB. Okay? So that means it's going to cut it into two congruent parts, two congruent halves. So then that tells us that angle CAD and angle BAD are going to be congruent, right? We can specify that. That's okay to do. And the reason that's okay to do is because it's possible to do, right? There's nothing, I haven't done anything strange or impossible there. All I've done is just add an angle bisector, right? Now, what's the effect of that, though? If I add this angle bisector, look what we accomplished. Now, I've got these two separate triangles. I've got the triangle on the top and the triangle on the bottom. You guys getting this over there?
Yep.
The triangle on the top and the triangle on the bottom. How many congruence marks do I now have on those two triangles? Two, right? I've got these sides are congruent, and I know that these angles are congruent. How many do I need to prove that the actual triangle is congruent?
Isn't the middle one?
I need three, don't I? And where's the other one?
The middle one.
Yeah, good. They share the segment AD, right? And so by what property then can I say that segment AD is congruent to itself? Yeah, the reflexive property of congruence, right? So now I've got three. Now by side angle side, I can say that the top triangle and the bottom triangle are congruent, right? Now let's write that congruent statement down. Triangle, if I call the top triangle, triangle BAD, that's congruent to, how would I have to say the bottom triangle? CAD, good. Right, because I have to line up the corresponding vertices, right? So now look what that does. If I show, I've just proved by side angle side that these two triangles are congruent, and so that's very useful to me because now, even though I only have 3 congruence marks on here that I've used so far, I know that if the triangles are congruent, all 6 corresponding parts of each triangle are congruent to the other, right? And so that also, coming along with that, I know that angle B and angle C are corresponding parts, and so they also have to be congruent, right? Now, what's my reason for that? If I've shown that the triangles are congruent, what's the reason that justifies saying, okay, well then angle B and angle C are congruent? That's it, CPCTC, right? Corresponding parts of congruent triangles are congruent, right? So by CPCTC, that's true. Okay, that's that's kind of a slick proof, isn't it? The thing that's different about this is that we added all this blue stuff on our own. We didn't start off with that. We just said, okay, this is going to help us out to draw in the angle bisector and use that. And it allowed us to create 2 smaller congruent triangles that helped us out, right? That helped us to prove that those angles have to be congruent by CPCTC, right? Okay, I just wanted you to see one like that, you know, and not that we're going to do a lot of that stuff this year in geometry, but if you go on in math, which I hope some of you do, then you're going to eventually see some more things like that, so. Okay, moving on. Some other stuff we know. An equilateral triangle, we said, is a special kind of isosceles triangle. Equilateral just means equal sides, right? So all the sides are congruent. Now we've got these corollaries to previous theorems here that allow us to make a relationship that you probably already know, but now it's official. What they essentially tell us is that if a triangle is equilateral, then it's always equiangular, and vice versa. And in math, here's the wording that shows us that. Whenever you see, thank you, whenever you see the words if and only if on a statement, that means it's like a two-way arrow. So that's saying that the condition of the triangle being equilateral and the condition of it being equiangular always point to each other. If one is true, then the other is true, and vice versa, right? And so we know, of course, that's always the case. If it's equilateral, then it's equiangular. All the angles are also congruent. Thank you. Okay? Make sense? So we get some stuff, and much of this is you would have, you know, it's just kind of common sense anyway. Now, here's something I do want to go through, though. I think this is kind of useful because there are lots of questions like this that show up on. Oops, that's not the one. This. There, cover that up. A lot of questions like this that show up on the reviews, and I'm not so sure on the homeworks, but I know they're on the review assignments and they're on the test. Okay, so we got to know how to deal with these. These are kind of like puzzles. Now, you remember, I think it was last chapter, I had some questions on the reviews and the tests where it gave you a big jumble of lines and whatnot, and it said, okay, if this angle has this value, then what's the measure of this other angle clear down here somewhere? And in the process of finding that, you typically had to go in and fill in a bunch of, you kind of had to fill in the pieces of the puzzle, and the more angle measures you got in there, the easier it was to connect them, right? This is similar to that in a way. If we want to solve for the values of x and y, even though they're far apart in this picture, they're going to have an effect on each other, right? And so I got to start maybe with one of them, but then use use the value of x or the value of y to kind of fill in the blanks in this picture to find the other one. Okay, now let's go through this. Do you see a way that I could solve for one or the other of those right away? And you got to kind of look at, the congruence marks are going to be important here, aren't they? That's telling us some side relationships. They're going to translate into some angle relationships for us.
Since all three of those ones are equal, then wouldn't it just be 60?
Okay, good. Now look what we got here. Good. We know that this blue triangle is equilateral because all the sides are congruent. Now what did we just say about equilateral and equiangular? Well, they go together, right? So if it's equilateral, that means all the sides all the angles are congruent, and so if this is x, then the other two are x also. But by the triangle sum theorem, what's the sum of the interior angles in a triangle always? Yeah, 180, right? They always add to 180. And so I can make an equation out of this. X plus x plus x, which is just 3x, equals 180, right? So what's x? Yeah, divide both sides by 3, and x equals 60. Good. And so we can actually write 60 in there then instead. Okay, so that's 60, that's 60, and that's 60, and that might be useful to us. Now, what do we know about the red triangle? Okay, so what kind of triangle is the red one? It's isosceles, right? Because I've got these two congruent sides. So now, what do we know about the angles in an isosceles triangle we just talked about?
Bases are the same.
Good, the base angles are congruent. So that's going to be y, and that's going to be y, isn't it? Everybody see that? Because those two angles have to be congruent, right? Okay, now that helps us a little bit, but we're not quite all the way there yet. We know our goal is to come up with some kind of an equation over here based on all the angles in this isosceles triangle. So we know that two of the angles are y. And so if they all add up to 180, I get y plus y, so 2y plus something must equal 180. If we just knew the value of that angle, the measure of that angle, we'd be set, wouldn't we? We'd have our equation.
To add 60.
Okay, so I know, I can find it, can't I? Because I know that these two angles, right, here and here, are a linear pair, and so they're supplementary. They have to add to 180. So if that's 60, this has to be 120, doesn't it? Everybody see that? Okay, now we're set. Because now I've got my equation. Y plus y, so 2y plus 120 equals my 180 degrees from that triangle. And so I can pretty easily solve for y here. Subtract 120 from both sides, so 2y equals 60. So what's y? Whoops, that equals. Yeah, it's 30. Good. Okay, make sense? All right. So you'll see some of those. They're all essentially, back strategies, how we deal with them. Okay, so the other thing that we get in 4.6, and this is kind of useful also, this is sort of broken up into little pieces, isn't it? The other thing we get in 4.6 is we add another congruence postulate. Okay, we've got 4 of them. Wake up, come on, wake up. We've got 4 of these already that work for all triangles. We've got SSS, SAS, ASA, and AAS. Okay. We get another one that's specific to right triangles, HL. Okay, this tells us that if you've got, come on in, thank you. If you've got 2 right triangles and you want to show that those are congruent, we have even a shorter shortcut. It says that the hypotenuse leg, or the HL is all we have to put. HL congruence theorem just says that if the hypotenuse and a leg of one right triangle are congruent to the hypotenuse and a leg of another right triangle, then guaranteed those triangles are congruent, right? And it's a shortcut, but it's kind of a disguised shortcut, because what do we actually know about these right angles also? I mean, right angles are all congruent, aren't they? Right? So we know there really are three congruences there that are sort of implied, but being as they're right triangles, we can sort of ignore the fact that those right angles are congruent and just focus on the hypotenuse and the leg, and that's useful. So that's another one that pops up in 4-6 that allows you to, take a little shortcut. What I want to do now is I want to look at one other thing. I want to look at an example of a problem. I can pull one of these up from the review, the first review assignment that I think people had a little trouble with. Okay, you get a bunch of questions like this on the review, and you'll have some on the test. They give you the three vertices of triangle ABC, and they're asking you to classify this based on the vertices. Now, there is a little built-in help here that you may not have recognized as being help at first, but it is. There are three spaces built in where you can actually calculate the lengths of the sides. Now, that's going to be useful when we classify a triangle. We're going to classify it, of course, in two ways. We're going to classify it by the angles and by the sides, right? And so this will help us to classify it by the sides at least. But then we got to also deal with the angles, and we're going to talk about a way to do that. So let's go through this one. Now, remind me real quick, if I want to find the length of the side of a triangle, if I know the vertices, how am I going to do that? Okay, and you're referring to, what do we call that? Distance formula. Right, so we need the distance formula. Okay, we're going to use the distance formula, and we know that the distance between 2 points is just the square root of x2 minus x1 squared. So the difference is between the x coordinates, right? Plus the difference in the y coordinates, y2 minus y1 squared, right? So we're going to have to do that for each of these cases. So we'll take, like, if we wanted to find, for example, the distance AB, well, AB is just going to be the square root of what minus what squared plus what minus what squared. So AB. Okay. Oh, say it again, right over here. Someone was saying it. How do I calculate the distance between A and B? What's x2? If A, we're talking about point A and point B, then point A we'll call point 1, point 2, B we'll call point 2, let's say. So 0, right? So the x2 just means the x coordinate of the second point, right? So we get 0 minus negative 5, so 0 plus 5, whoops, sorry, made a little mistake there. Squared, right? Squared goes outside. Plus, what's y2? No, we're just looking at A and B.
Oh, just kidding. I'm at 2.
2, okay, so 2 minus 1 squared, right? And so if we simplify that, 0 plus 5 is squared? 25, okay, so square root 25 plus 2 minus 1 is squared? 1, so 25 plus 1. So AB is just the square root of 26, right? And we could put that into our calculator and get a decimal answer. They want us just to round to the nearest hundredth, right? Okay, so we'll do that. Okay. Okay, so if we want to calculate the square root of 26, we can do that easily. Square root of 26 is 5 point, to the nearest hundredth, what is that? Yeah, 5.10, right? Because if I go out 2 decimal places, I have to go 1 more to see if I round up. So 5.099 rounds up to 5.10. Okay, so we get then, and what's that kind of a wavy equal sign mean? Approximately, right? Because we're rounding, aren't we? So 5.10. Okay, while we're at it here, let's go ahead and calculate BC. Okay, so BC. Now, if I cover up A and I use these 2 points as point 1 and point 2, right? Doesn't that just give us, we'll go through this a little quicker. So 3 minus 0 would be x2 minus x1 this time. Everybody agree?
Yeah.
So we get 3 minus 0 squared plus negative 2 minus 2 squared, right? So 3 minus 0 is 3 squared. Negative 2 minus 2 is negative 4. Okay, but remember our little trick? Do we ever square a negative? What do we do if we're squaring a negative anytime ever?
Take off the name.
Yeah, square the positive so we don't make a mistake. It's easy to make an input mistake if you square a negative. So negative 4 squared is the same as positive 4 squared. And we end up then with, if we do the math, the square root of 9 plus 16, right? 3 squared plus 4 squared. That's the square root of what? 9 plus 16? 25. So what's BC? 5. Exactly 5, right? And then finally we got to calculate AC. So let's do that. Last one. If I'm doing AC, I'll just cover up B. So there's point 1, there's point 2. So I get the square root of 3 minus negative 5. So that's 3 plus 5 squared. Negative 2 minus 1 squared. So that's the square root of 8 squared plus, instead of negative 3, we'll make it positive 3 squared. So 64 plus 9 is what, 73?
73.
Okay, so we need to find, let me pull up our calculator and we'll see what that is.
What?
So that's 8.54.
Oh.
All right, so what does that tell us about this triangle so far? If we're going to classify that by the sides of the triangle, what kind of triangle is it? Scalene, right? All the sides are different. Now, what if this had ended up being exactly 5, and that was exactly 5, and that was 8.54? What would it have been? Isosceles, and then obviously if they were all the same, it would have been equilateral, right?
Right.
Okay, so we know that we want to do the angle part first, so it's some kind of scalene triangle, but we know that the second pull-down menu, we would have just chosen, oh, whoops. We would have just chosen scalene. But we don't know what kind of scalene. What are our options? Could be acute, could be obtuse,
Yep.
or what's in between the two?
Right.
Could be right. Okay. How do we know which one it is? Any suggestions how we could figure it out?
Draw it.
Well, we could draw it, but if we draw it, our drawing is not going to be good enough. What if the angle is 90.03 degrees? Are we going to be able to see that on the drawing, that that's actually obtuse? Probably not, right?
I would just guess.
Guess, no, we only got a 1 in 3 shot then, that's no good.
Yeah.
Yeah,
You
no.
have to have,
No,
stuff. Or you could get it wrong twice, and then you finally get the right answer.
But on a test, that's not going to do any good. What do you think? Yeah, think fast. Okay, now how about this? We know if we think about, let's think about the in-between case, the middle case, which is a right triangle, right? What do we know about right triangles? Remember from our previous discussions of right triangles, we always know in a right triangle, if the legs, we'll call them A and B, and the hypotenuse C, what's the relationship between A and B and C in a right triangle?
A squared plus B squared plus C squared.
Yeah, right? We get the Pythagorean theorem. So we know that the hypotenuse squared equals the sum of the squares of the legs, right? And so if I wanted to find out what the actual length of the hypotenuse is, how would I get that C by itself if it's being squared?
Square root, like 5 square root.
Well, how do I undo a square?
Square root.
So I could square root both sides, right? So I could then just get C equals the square root of A squared plus B squared. By the way, that looks a little familiar, doesn't it? Doesn't that look a lot like what we just did? That's just the distance formula. That's all it is, right? Because if I know that, you know, A is really just gonna be the change in Y in this case, isn't it, between these 2 points, right? That's just Y2 minus Y1, right? And B is just the change in X, so that's really just X2 minus X1, right? So that is just the distance formula. Just, you know, masquerading as something different, it's really not. So we've got this formula that we get from the Pythagorean theorem or the distance formula, take your pick. We could take our last example up here and we know the side lengths, don't we? Now in a triangle, I want you to visualize something else here too. There's one other relationship that we need to be aware of that's you'll get right away. If I've got a triangle, let's say, I'm just going to draw it like this so it's not drawn to scale. Let's say I put in some side lengths. This is going to be 4, this is 5, and this is 6. Okay, those are the lengths of the sides of that triangle. Could you tell me, if I label the angles in here as angle A, B, and C, can you tell me which of those angles you suppose is going to be the biggest angle? That's supposed to be an A, and that's a B, and that's a C. So which angle, A, B, or C? That's where you hit the 7. Which of those angles is going to be the biggest angle?
C.
B.
No. B. No?
A.
Yeah, it is A. How come?
We just 4 and 5 each numbers.
Well, no. Because now, doesn't it make sense that, and this is true. This is always true. The biggest angles in a triangle always are going to stare across at the biggest sides. And that makes sense, doesn't it? In order to make a big angle, don't I have to take the opposite side and stretch the opposite side out?
Yes.
Okay, so we know, because 6 is the biggest side length, we know that angle A is the biggest angle. What's the smallest angle here, guaranteed? Well, so it's going to be B, isn't it? Angle B, because B looks across at the shortest side in the triangle, right? Everybody agree? And then the medium angle, the one that's in between, is going to be the one opposite 5, so that's going to be C, right? So if we take our situation up here from before, we've got the side lengths 5.1 and 5 and 8.54. So if this thing were going to be a right triangle, which of those 3 sides would have to be the hypotenuse? The hypotenuse is always the longest side in the triangle, right? In the right triangle. It'd have to be AC, wouldn't it? Right? So why don't we do this? Why don't we ignore what AC actually is, and let's calculate what the hypotenuse would actually be if this were a right triangle. And we'll compare what we calculate with what actually we have, right? So if I take the sides 5.1 and 5 and calculate which hypotenuse, what length hypotenuse goes with those, then we'll know. We'll know if ours is either right on the money, right? So it is a right triangle, or if it's too big, that must make it obtuse, or if it's too small, it must make it a cube, right? Let's see what we get. So we'll go back to this page, and this is what we want to do. We want to calculate C, what the hypotenuse would be, right? So if we plug in the square root of 5.1 squared plus 5 squared, because those are the lengths, yeah, you bet, those are the lengths of the legs. What do we get? Let's pull up our calculator and see.
Okay. Let's see.
Come on, let's go. Oh, let's go. Okay, so the square root of 5.1 squared plus 5 squared is 7.14, if I round to the hundredths place, right? So C, 7.14. So if I draw this right triangle then, I've got the 2 legs of length 5 and 5.1. What if those are, say those are sticks, and I've got a hinge down here at the bottom that's hinging them together so they can move. And then I'm going to stretch a rubber band across that gap. If we make this a right angle, the length of that rubber band is gonna be 7.14, right? Because that's the hypotenuse that goes with those legs. If the legs of the right triangle have these lengths, then that's what the hypotenuse has to be. Now, in reality, we found that the third side of the triangle was something bigger, wasn't it? 8 point something? Something like that, right? But it was bigger than 7.14. So what would I have to do to that rubber band to make that side of the triangle longer? Yeah, I'd have to stretch it, right? I'd have to take this hinge, I'd have to pull the sticks apart a little bit. What's that doing to the angle? It's changing it, and it's making it bigger than 90, so it's making it obtuse. Aha, right? So now we know, if we go back to our problem that we were working on, because this is bigger than the 7.14, which is what the hypotenuse would have had to have been, we know it's obtuse. Now, what if the hypotenuse that we had calculated for these two legs was exactly, what if we had calculated a number of 8.54?
Right.
Then it would have been a right triangle. What if we had calculated a length that was bigger than what we actually had? So let's say that this length was something like, for whatever, to say we calculated it to be 10.1, and what we actually had was 8.54. Doesn't that mean that the rubber band's going to have to shrink a little bit and bring those angles in? Does that make sense? It's kind of a good strategy, huh? So we can always just compare what we actually have with what the hypotenuse would need to be. And that tells us. So in this case, it's obtuse. Okay? We good?
Yep.
All right.
Oh, we have like 6 minutes left.
So there's no point going anywhere. Okay.
I think we should.
Think we should? I don't think so.